Question 9. You've got a 5 gram sample of potassium chloride added to 50 grams of water that's initially at 20 degrees C. The mixture is stirred and potassium chloride dissolved, the temperature decreased. Describe the steps you would take to determine the accurate minimum temperature not influenced by the surroundings. So normally the kind of experiment you're doing is to work out a temperature change, and then you can use delta H equals minus MC delta T. So if you're trying to find a temperature change, normally you carry out this procedure. You'd add the water, the 50 grams of water, to an insulated beaker with a lid. Start a stop clock, take the temperature of the water for 3 minutes. Don't do anything at time 4, or don't take any readings at time 4 rather. At time 4 you're going to be adding the potassium chloride to the water and stirring. You don't take the temperature at time 4 minutes because that's when you're adding the potassium chloride and stirring. Continue to take the temperature each minute for at least 5 further minutes. Plot a graph of temperature versus time. Extrapolate, which means extend the lines, the first line forward to 4 minutes and the second line backwards to 4 minutes, and then measure the two temperatures and subtract the two temperatures to find the temperature change. That's the normal standard experiment, and then using that temperature change delta T, you can use delta H equals minus MC delta T. However, the question is slightly different. It's told you the initial temperature is 20 degrees C, so you don't need to do the first step where you're measuring the temperature for the first 4 minutes or 3 minutes and then adding it. You can ignore that step because you know the initial temperature is 20 degrees C. You're not actually asked to work out either the temperature change. All you're asked is for the final temperature. So you can amend this so that it looks like this. You add the water to the insulated beaker with a lid, and you start the stop clock, add the potassium chloride and stir. So you don't need to work out the initial temperature. Take the temperature each minute for 5 minutes. Plot a graph of temperature versus time, and then extrapolate your line back to see where it hits the time when you added the potassium chloride. And then just take that time. So you're not even asked to work out the temperature change, so work out the new temperature, take away 20 degrees C. All you're asked to do is extrapolate the line back and calculate the temperature when you added the potassium chloride. Question 9.2. The temperature of the water decreases to 14.6. Calculate a value in kilojoules per mole for the enthalpy solution of potassium chloride. Okay, so Q is MC delta T, or delta H equals minus MC delta T. So delta H has got the minus value in because delta H has a minus value, expecting it to be exothermic. Q doesn't have that value, and you have to put the plus or the minus in at the end, depending on whether it's exothermic or endothermic. M is the mass of the liquid that's used, 50 grams. Delta H equals minus MC delta T, so you've got minus 50 is the mass of the liquid. C is the specific heat capacity, which you're already given, 4.18 joules per Kelvin per gram. Multiplied by the temperature change. Well, the temperature change has gone down from 20 to 14.6, so it's gone down by minus 5.4. The minus means the temperature has gone down, and when you multiply all those out, you end up with 1128.6 joules. You know it's in joules because the specific heat capacity has got joules as one of its units. You can convert that into kilojoules, or I'm going to do that at the end because it asks for it in kilojoules in a minute, but I'm going to do that at the end. Now I've got to work it out for 1 mole. Well, the MR of potassium chloride, potassium's 39 and chloride's 35.5, so it comes out as 74.6 moles of potassium chloride is the mass divided by the MR. The mass that you've got is 5 grams. Divided by 74.6, I've got 0.0670 moles. I've got a lot less than 1 mole. So this is the amount of energy that's taken in. So that's the energy that's gone down because it's an endothermic reaction. It goes down, so that's a positive value. So that's the amount of energy that it's gone down by when you've added 0.067 moles. Okay. So now I've got to scale this to a value, or imagining that you had 1 mole. So what I do is I do 1 divided by 0.670, gives my scaling factor to imagine what the enthalpy change would be for 1 mole, and I multiply by 1128.6. So it's 1128.6 multiplied by 1 divided by 0.0670, and that turns out to be 16,839 joules per mole. So I've worked it out per mole now, so by scaling this value up. I now need to put it into kilojoules, so going from joules into a larger unit value of kilojoules, I divide by 1,000, so that turns out to be 16.839, and I've got to get it to three significant figures rather, because everything else is to 3 significant figures, so it turns out to be 16.8 kilojoules per mole. The enthalpy solution of calcium chloride is minus 82.9 kilojoules per mole. The enthalpies of hydration of calcium ions and chloride ions are minus 1650 and minus 364 kilojoules per mole respectively. Use these values to calculate the value of the lattice enthalpy of dissociation of calcium chloride. So what actually happens? A lattice enthalpy is the energy required to break a lattice. And so when it dissolves, what you actually do is the enthalpy of solution is the value required to break the lattice, which is the lattice enthalpy, but you get some energy back, so you're going to need some energy to break the lattice, but you get some energy back when these particles hydrate, in other words, bond to the water, a process called hydration. It tells you these values here. So my enthalpy of solution is the process of dissolving the solid, so the enthalpy of solution is minus 82.9, and that equals the lattice enthalpy, the energy required to break up the lattice when it dissolves, plus the energy that you get back when it starts to bond to the water. So minus 82.9 is the lattice enthalpy added to the values of the hydration when they bond to the water. Now in calcium chloride is CaCl2. You know that because calcium's in group 2 and forms Ca2 plus ions. Chloride is in group 7, forms Cl minus ions. So calcium chloride is Ca2 plus Cl minus, but you need 2 Cl minuses to balance out the Ca2 pluses, so it's CaCl2. So I've got 2 lots of chloride ions, 1 lot of calcium ions. So I've got the enthalpy of solution minus 82.9 is the lattice enthalpy added to minus 1650, which is the energy that I get back, the energy that's released when calcium ions bond to the water when they get hydrated, and 2 lots of minus 3640 because there's 2 moles of chloride ions in there. That ends up as minus 82.9 is the lattice enthalpy plus minus 3300. Take that across to the other side. 3300 minus 82.9 is 2295, and it's in kilojoules per mole. Explain why your answer to 9.3 is different from the lattice enthalpy of magnesium chloride. Well, you've got to look at the size of the ions, or the difference between calcium and magnesium. Magnesium's a much smaller ion. It's further up group 2, so it's got 1 less energy level, 1 less electron shell. So it's a smaller ion, and a smaller ion will attract the calcium ion more strongly because the particles, the ions, can get closer together and form a stronger ionic bond.